what is the solute? What was that? State is being solved. Okay. So, and the benefit of using molarity or these concentrations, things that are in solution, is that it makes it easier for us to transfer. Right? So, like for instance, how do you guys make cooling in the concentration? Is it going to see the little squeeze bottle cooling? Or VGS, right? So that's an example of us using something that's very concentrated and moving it. Okay. Now when we go through that process, and we talked about it, we have C1 V1 equals C2 V2. And I think if you're both going to use ML, right? Same concept, whereas C represents concentration. V1 of our initial. V1 represents the volume of our initial. C2 represents concentration. What we want, or honey. And V2 represents the volume. Okay? So we know that we can go with something that's very concentrated and something that's less concentrated. Right? You guys are familiar with vinegar, right? Vinegar is just an example of diluted acetic acid. So typically when acetic acid is made, it's a byproduct of a bacterial process. And so typically anywhere from 25 to 18% acetic acid. Okay. So that brings us to another form of concentration, percentage, right? So we have percent mass, or percent volume, or percent molarity. Right? So in that context, when we talk about percentage, it would be specific over the total. Okay. So specific, in this case, we're talking about acetic acid. So we're looking at the mass of the acetic acid and the total mass of the full mass. That is the total mass of the full. Right? So in this case, we're looking at acetic acid. Acetic acid. And that's what we must understand. Now, this is also a form of concentration. It's one of the things that a lot of biologists study. The other thing that biologists like to use is the concentration of, call it 10x, where x represents whatever thing we're working with. So you're making it 10 times more concentrated than you already have, right? And so you want to add 1x. Right? Now, this is done in labs that don't like doing chemistry, right? So they don't want to use molarity because molarity is not. A lot of people are familiar with working things that are 10 times. Makes sense. If it's 10 times greater, and I want to make it 1x, I have to make a 10 mil solution. How many of that 10x? right now. So if something is 10x, you have 10x of this concentration. And we know that 1x is a working So if I want to make 10 mils at 1x, how many mils of my 10x will I need? So 10? Yeah. Okay, the way it works is, again, we're going to be using this equation, right? We want 1x, 10 mils, right? So that's going to be what we want finally. So if we go C1, V1 equals, in this case, it's 10 mils, 1x. And we know that our concentration is 10x, right? We just solve for V1. So what is V1? 1. Okay. So the volume will be 1 mil, right? Does that make sense? Because it's 10 times greater, right? I only need 1 mil to sit there. So, like I said, these are often used in biology. I'd say that biology is chemistry, but often they always say, oh, it's the math, it's the math. So it's cool. And so you'll often have biology that describe everything as 10x, 20x, 50x. So, because it's a lot easier than working with this numbers. Okay, questions? Concerns? Chat? Okay, so molarity is a form of concentration. Percent mass is a form of concentration. I'll give you guys examples. Now, we also have these are just examples. We can talk about how to make a solution. Definitely talk about the pictures first. Okay, so if you're making a solution and you're making it to a certain concentration, right? You always want to start off with your solid first. So make a solid first. This here is called a volumetric glass. It's perfect, right? It's very low percent air. That's a nice little line that's drawn around the parts of here. Right here. You go up to that volume. Perfect. You don't want to go over that volume. Chemists love these types of glass. The reason why chemists love these types of glass is because they're perfect. They keep you from overshooting, right? Because there's a tendency you have other big groups or things that you always overshoot rather than going exactly to that volume. Okay, so the first thing that you always do is you put in salt, and then you put in your water up to that mark, and that gives you that perfect volume. Okay, so you notice this is a gradient. Because they want it to be gradient, they want to make 1,000 milliliters of this solution. Perfect. So the reason why we do this is because there's a tendency of us when we make solutions, we'll put the volume in first. Volume is 1,000 milliliters of water. That's your first thing. That's not what you want to do, because if you look at this definition, it's the sum, it's the total, it's liters of solution. So solution is water and salt. Right? It's not just the water. So our first instinct, they don't have 1,000 there. It says a liter, right? 1 liter. My first instinct is I'm going to 1,000 milliliters, right? No, that's not good. We want to bring it up to 1,000. Okay. So again, start with a solid, and we bring that up to the wall. Okay? And that's crucial. You don't know how many students that you'd be in the middle of the experiment and you're wondering why it's not working. Right? And we're talking about, diagnostic type of situations. And I'm like, man, if I tried right now, I said I should have a value my control percent, which react at 5 millimeters. Nothing happened. I'm at 7 and 8, and all of a sudden it starts to work. What's going on? And that's because most students, first think about it, they go with their answer. Oh, I'm just gonna put in 1,000 millimeters, right? But because I think of it, don't think of it as a solution. That solution means all you can solve it, right? It's close. So we need 1,000. Does that make sense? You see it? And I'm making a big point on it because I guarantee you guys have a solution that I'm asking you guys to do probably a couple of days. That somebody's going to do it. It's one person. And he already wants it. Okay? So, let me break it down. The reason why this works out, because at the end of the day, the number of moles for C1B1 is going to be equal to the number of moles for C2B2. They're going to be equal to each other. So we can set them equal to each other. Because the moles are going to be the same. The only thing that happens is that we're diluting substance. So we're adding more water to the. Okay? So if we think about it, N represents the number of moles, M represents the molarity, L represents that mole. Okay? So, or liters, right? So we have liters are going to cancel out, and then we're left with just the number. So again, N1 is 2, and then that's going to be ML1. It's going to be equal to M2L2, which we can make it very general in terms of concentration. Okay. So here's an example. Go look at the answer, right? Look at the problem. Every time I fix it, it doesn't seem the same for something. I think I have like 50 copies of it. Okay, so if 0.850 liters of a 5 molar solution of copper nitrate, CuNO3, 2 is diluted to a volume of 1.80 liters by the addition of water. What is the molarity of the diluted solution? So in this case, again, we're going to see B1 equals C2B2. And then in this case, we're solving for C2. Okay? So in that situation, all we do is just plug in the concentration of C1, and then multiply it by volume of C1, and then divide that by volume of C1. And that's going to give us our concentration. Simple, not too hard. Okay, let's see if we can make it a little more challenging. You guys a problem. Then I actually you guys a quiz. Where should we start? Okay, so how would I find out the numbers? Okay, so what is the molecular mass? Okay, so we have 16 grams NaCl over 58.44 grams. Okay. Then, like my number of moles.
I think
There you see moles. Yeah. So we have 1, 9, 8. Polarity. Okay. And then, what about percent? Mass. Okay. Now, meters. Okay. There's specific, which is gram per and where by that line. What was that? We did. Yep. Oh. No, because that's it's the ratio, right? No, it is part of the soil solution. It's already incorporated because your density is the density of that solution. So it's 1.1. All right, all the density of the solution. That's all right. And that was the important. That's why I erased water initially. Right? Oh, nice. I didn't see that. Okay. So then I give us a density of our solution. Right? So my question is, sig figs. How are we doing sig figs? Right now, sig figs work. Sure. What's that? Okay. So, and then right? Questions, concerns, cash, or actually no, really should be 1. Then I said 1,000. I said 1,000. I didn't put a decimal there. So technically, if you want to be here, okay, or for the polarity, 2 molar, right? So discussion polar, and then discussion. It's 1 sig fig, 2 11. Oh, because I said 1,000 no decimals. So when we do this, how many sig figs do we have here? So I pull myself, my decimal. Okay? You guys see that? So the thing is that we use 1,000 here, there's 1 sig fig here, right? So then this will be 1,000 here for that answer. So then again, so 1 sig fig. Okay, what was that? Okay, so the second part. So if so this is our stock solution. How many millimeters will to make 0.002 molar at 100 mils? Yeah, 1,000 mils. Okay. So then we're solving for what? Okay. Like all that work for me, like usually cheated. Hey, ever done that, right? See how it works? And the funny thing is that we used to work a lot. Then figure out I lot. You make a lot of this. You always have to make all this stuff. Sometimes you have to be fresh. Or if you decide you're going to be a doctor or a pharmacist, you have to sit there and do. You'll have stocks and stuff. Then you'll have a stock to work with down and a working profit. Split that out with that. Or you another. How many of you guys put like who's rate all those things? Have you noticed that they've gone to the concentrated? So I really cash is going to the store. You got to be concentrated. And then I told them, so go ahead and put something in the and so he puts it in the yeah, so they're concentrated. Right? So you know, right. He puts it, you know, I I'll grab him. Don't face. What are you what's that? There's no water, it was all concentrated. Big, everything. So it's growing. Food. And so as a result of this, right, I know that. I said, what? Oh, can't help you, right? Call my dad. And culture. At this place. And in summer. But I wasn't in California. I grew up radiated. Literally. Just had and so then I and then yeah, this is great influence and stuff that I do that I figured, all right, okay. And he's like, yeah, no, I need a message for me. And he's like, well, he was concentrating. I didn't know about the concentrate. And then he's like, I noticed that I had to buy so you put concentrated radiator for my God. Don't figure out what's wrong, right? Too bad it cost me quite a bit to fix it. But that's another example of the life where we go with the loop, and as a result of it, we cause problems. So let's move forward. Then you guys is So there are other things, like I said, other than polarity. Polarity is the one that's confused. The other one we talked about is mass percent. Does the mass per component or the mass of the solute equal carbon 100? So another example is liquid. So 7.4% sodium carbonate, or sodium hypocarbonate. The other one that is often used as well is percent volume. So that's volume of solute or volume of solution. So we're making alcohol. Sometimes we get crazy and get, like this. So we can do mass over volume, where we use the mass over volume by that. Mass. So a lot of times it's again life sciences. So when we're talking about state, they get mass. So in this case, mass salt over volume space. But so that means they zero mass per volume. Let's so this here is volume. So that's the same bag, 0.9%. And then with typically your capacity it should be around 70 to 100 grams per deciliters. So that is another example. The last one is parts per million and parts per billion. Now these are often used in those poisons. So like for instance, how much arsenic do you want? So in this situation, we're looking at very small quantities, and then we're putting them in very large solution. For instance, arsenic is poison, right? And so too much arsenic, then it kills. Right? So there's a range of arsenic that can add to the water. You have all of these minerals that exist. None. The reality is that arsenic. So we have to account for this. Okay. So we'll use parts per million or parts per billion. And the way that we calculate that is that we have the mass of the solute over the mass of the solution. And then we multiply it by 10 to the 6 for parts per billion. 6 per billion. And then for parts per billion, we multiply it by 50. Okay, so as I said, our water system is not safe, land, and water. So speaking of this, the amount that is allowed is 1 part billion. And that's down water emissions. Five. Thousand. Yeah, so it's so it's sort of ridiculous concentration. And we know that the effects small things causing the effects of kids. So so after we have our tap systems, we have to just for that, so we have a filter system. How you guys doing? Fine. So that conversion. So you have more questions. Let me see what I can do for you. So was it scouting it up?
But it's still the wording
The business. Okay. So what we're gonna do is I'll pull up a couple of questions. I'm gonna give you guys a few minutes. And I won't get started with the next chapter. Tuesday, Thursday, it's all the same, right? So I'll give you guys a short break, and then what we'll do is we'll finish up the last finish. And so you guys can help us with that. And then we have 2 labs to start. So 2 labs require some labs. Guys are actually going to be strictly on protocol labs after this. So so the first thing that you're going to do is that you're going to take your magnesium. You're going to weigh it. You're going to file it down or send it down and weigh it so that you end up with 3 grams of magnesium. And you're going to use stowable sit there and get on all of the oxidized. All right. You're going to be oxidized. And so, and the key is that we want you to get. So you already have one side oxidized. It's hard to get that in. So that's important. Follow down to also getting magnesium oxide. So you guys are going to be basically making magnesium oxide by using oxygen here. But you want to be careful because so we want to keep the magnesium overnight, but yet you still want the gas. So you guys are going to use the first one. And so for those who have heated acids, it's a big old one. Together. Okay. So what we'll do is we'll let you go ahead. Others still working on it. And then you guys can come on. So the goal is to be done before 3 o'clock. Really kind of and so we want to get down there and get our seat. I see that. They're not going to hurt your audience. But I still want you guys to meet those. So that you have the price. All right. Okay. What was that? Yes. What do you got? First. I know you don't receive with us. I want you guys to recognize you guys for this. Let me have a class. Thanks for experience. So we got to try to get this right. You know, I want you guys to also that you guys are representing the science, right? I hope you have some more stuff to understand. Actually, that knowledge. And the order department helped me out. They make my life real easy. They get a lot of the problems. They're all of the so any day now, but now we're just looking for witness. And the other and our compressor is working, but they're not working out. And we have hot water. Here. Right. So let's go take a quick break. Come back in 6 minutes. But then we'll come back and